the last block is gamma, gamma sampling. Okay, the to sample gamma k that we have to derive is full conditional distribution. Okay, and this is the definition of the full conditional distribution of gamma k. Okay, okay here. So this is definition of the full condition probability or probability mass of gamma k. Okay, so then this gamma k minus the subscript minus k is the vector of gamma k except vector of the indicators except gamma k. Okay, so this is the full conditional. Okay, and then you will see that this full conditional is just conditional probability of gamma k given beta k only and nothing else. And the other parameters and data have no additional information. Okay, to see this, we are going to just the analytically derive its full conditional density or the full conditional mass. Okay, again, this is the definition of the full conditional probability. Okay, and then here by the Bayesian rule, okay, this probability should be proportional to the product of likelihood and prior densities. Okay, so this is prior density of gamma, this prior density of the beta. Okay, in gamma there are capital K gammas, and here capital K betas here. Okay, so then you see let's take a look at here, and where is gamma k? Where is gamma k? There is no gamma k here. Okay, because y does not depend on gamma k once beta is given. Okay, once beta is given, then y is independent of gamma k. Okay, yeah. So that's why this term should be disregarded. Okay, and because the gamma k's are mutually independent, we need to keep only the probability of gamma k, and the other parameters of the other probabilities for the other gamma k's are irrelevant here. Okay, and same for here, and there's no gamma k's here. So that's why there are only two terms: probability of gamma k and probability of beta k given gamma k. Okay, right? So then gamma k can take either 0 or 1. Okay, so then probability of gamma k equals 1. This full condition, right? And then again, this is just proportional. So then the other quantities are just normalizing constant. So constant times probability of gamma k equals 1, and then the probability or prior density of beta k given gamma k equals given that gamma k equals 1. And then this is full conditional that beta gamma k equals 0 is just normalizing constant times prior probability of gamma k equals 0, and then the prior density of beta k given that beta gamma k equals 0. And then their sum has to be what? Their sum has to be 1, right? Has to be 1. So then sum of these two quantities should be 1. It means what? It means what? This normalizing constant should be 1 over this term plus this term. Okay, and then now this normalized constant is plugged in here. Okay, so then finally we have the full conditional probability mass of gamma k. Or alternatively, you can use the Bayesian. This is full condition of gamma k, right? We know this. And by the Bayesian, we have this, right? Just apply the Bayesian, okay, as always. And then probability of beta k is the sum of these two conditional densities. Gamma k is generated, zero gamma k is generated first, and given zero gamma k and beta k is generated, plus one gamma k is generated first, and given gamma k, beta k is generated. Okay, so then this is the probability of beta k. Okay, I would say unconditional probability of beta k. Unconditional probability of beta k is the sum of these conditional probabilities. Okay, and here, then what's the value of this term? This is what? This is what? This is prior probability of gamma k. Prior probability of gamma k. What is the prior probability of gamma k? It's p. Prior probability that gamma k equals 1 is p. And 0 is what? Probability that gamma k is 0 is what? 1 minus p. Right? That's right? Right? So then this term is p. And this term is p. And this term is what? 1 minus p. Right? So p, 1 minus p. What about this? What about this? This is what? This is what? This is prior probability of beta k, given gamma k equals 1, right? This is here. Normal density. Normal density of beta k, right? Given gamma k equals 1. Because gamma k equals 1, then the mean is 0 and variance is b1. What about this? What about this? This is prior density of beta k when gamma k equals 0. So then this is a normal density. Mean is 0 and the variance is now b0, right? Right. So then this is the full conditional probability of gamma k. Gamma k equals 1. And then probability that gamma k equals 0 is 1 minus the probability gamma k equals 1, right? So then how to generate gamma k using these probabilities, okay? So again, this gamma k is discrete, not continuous, right? Sigma square and beta are continuous random variable. Meanwhile, this gamma k is a discrete random variable, right? So then we have to sample gamma k with gamma k will take 1 with this probability, and gamma k will take 0 with this probability. Okay, and to sample beta k to sample gamma k, just draw a uniform draw and just sample from this uniform distribution. Just get a uniform draw, and this uniform draw is defined over this interval 0 and 1. Okay, and suppose this is 0.7. This is 0.7. The probability that gamma k equals 1 is 0.7. Okay, and then what's the probability that the uniform draw is less than 0.7? Less than 0.7. It's 0.7, right? What's the probability that the uniform draw is less than 0.2? The probability is what? 0.2, right? So then if you try to generate gamma k equals 1 with this probability, then just get a uniform draw from this uniform distribution. Okay, and if the sample is less than this probability, then gamma k will take 1, otherwise 0. Okay, this is how to generate gamma k. So then the the first step is to compute full conditional probability mass. Okay, this is the first step, and then the second step is the just take just a uniform draw, and then the third step is that if the sample or the uniform draw is less than this full conditional density, then gamma k is assigned one or otherwise zero, right? And then this is repeated. This is just repeated for all gamma k's. Okay, okay, right. So this is how to generate a gamma. Okay. So then by using this procedure, we are going to we can sample the vector of the gamma case, which is capital gamma. Okay. Then we go back to the first step to sample beta from its full conditional distribution. Okay. All right. Then that's it. So then in each keep sampling cycle, we are sampling beta, sigma square, and gamma, and this gamma will be used in sampling beta in the next iteration. Okay, in the next iteration. Okay, all right. Okay, so then this is the beta abstraction. Okay. Okay. I think I should give you more intuition. Okay, let's go back to here. Okay, here. Okay, suppose beta k is close to zero. Okay, suppose beta k is very close to zero. Okay, let's see what happens if this is zero. This just simply is zero, simply zero. So then which one is bigger? This one and this. Oh, sorry, this one or this one. Which one is bigger? This is zero. Beta k is zero. So sk is not important there. Okay, this is zero. Okay, this is zero. And beta k is zero. Then which one is bigger? This normal density or this normal density? This one must be bigger, right? Because B0 is smaller. Okay, let's go back to the figure here. At zero, here. This density is here, very high, but the density from this normal distribution is very low, right? Relatively, right? Okay. So then that means what? That means what? So then this term is small, but this term is very large. So then this term will be what? This value will be small or large. If close to 0 or close to 1. It will close to 0, right? It will close 0. So then this value is very small, say 0.05 or 0.01. Okay, suppose this the point 0.01. Suppose this 0.01, 0.01. And then in the next step, we are going to get a uniform draw. Then the draw is most likely it will be larger than this value, because this value is just 0.01, right? So then that means what? Gamma k is what? Gamma k is 0, right? Gamma k is 0. Okay. Once gamma k is 0, then what happens in sampling beta k? What happens in sampling beta k? Here, this is 0, this is 0. Then the prior variance is now B0, and prior variance is B0. Then price B0, then this full conditional variance also will be close to 0. Okay, so then then that's it. Then beta and this the beta k sample from this full conditional distribution would be very close to 0, unless the data is very informative, and then it suggests that sk is important. Okay. right? Okay. And in contrast, if beta k is beta k is highly non-zero, and this is far from zero. Okay. So then what happens to this density? Okay. Okay. Let's go back here. Okay. So then if beta k is here, if beta k is here, so then this is literally zero. Okay. This is literally zero, and here is, and then the density from this normal distribution is quietly non-zero. Okay. So then what happens? Then what happens? So this term is zero. This term is zero. So then this term will be zero, right? So then what happens? This term divided by this term, but these are the same. These are the same. So then that means what? This value will be close to 1 or 0. This term will be close to 1, right? So then this uniform draw will be less than less than this value most likely, right? So then gamma k will be 1, right? Okay, right, right, okay, right. That's it. Right, right. That's it.